That's hilarious.
It's like, literally expired.
So for
The last step would be
like if you look like there's only one person. All like the classes.
You not ever use it until you get lunch.
Normally bring something or. It counts for credit hours. It's every credit hour. And it's
Good morning, everyone.
Occasionally.
Good morning. Okay, may I have your attention, please? Now I'm going to teach you. So this is implementation. I'm sorry, this is very messy here. Not messy on my slide. It's messy on the whiteboard. So how can we implement this the MATLAB trained ANN in our this IR, or not just IR, in other environment? I want you to hear to listen to me carefully, okay? Because we might have several problems based on this this diagram. So in the IR, in our project lab report, and I ask you guys to implement. This is the weight values and the bias values, and for ANN that has only one single hidden layer, and how to implement them. And here is the diagram. I posted this diagram on the canvas at the very beginning when we learned that this is the ANN, so you can have access to it. I'm sorry. So suppose this is the one input, we have one input, and we have one output. So this is in the middle, in the hidden layer, we have, suppose here is a without loss of generality, and here I use 25, but in our report we use 30, okay? It's the same thing. So I have so many the hidden layer neurons. So each of these connections, you can see each of these connections, and we have weight values. So we weight values, and I use this one to denote for input. Input weight value number 1. So here is input weight value number 25. Right? So so for this output value, I use O output W1. And so on and so forth, I have output W25. So you should know. So this is weight values, and these weight values, and they are from the MATLAB program. Right? So also, for each of these is hidden layer neurons, and we have a bias value. We have a bias value. The bias value, I do not know. Honestly, I do not know why MATLAB used this word. The bias value here actually is the negative of the threshold value we talk about for the neuron, okay? But the MATLAB, they want to use the bias, this is a concept, totally fine. So each of these nodes, they have a bias value. For example, B1, they have bias value for the first hidden layer neuron, and B25, and this guy is the bias value. And for the last one, for this diagram, for our case, we have B30, okay? Also, this output is also a neuron. Output is also a neuron, and the bias value is named as a BO. Bias for the output value. Questions so far? No question? Okay, then I'll talk about and how it works. And so how it works determines on how we can implement the ANN, and we obtain it from MATLAB into any other engineering applications. Right? First, I talk about the concept of normalization. I may ask you guys this in the final exam. What is normalization, guys? If you have taken FEM with me, for example, Jessica, you took FEM with me, right? Yeah. I told you how to do the normalization. Yeah. So mapping, right? Do the mapping. And how to do the mapping? And I need to tell you is this. So And suppose this is x minimum and x maximum. I'm talking about single input. And so x minimum value and x maximum value, and they are physical quantities. Right? And this one can be, this is an electrical signal, can be acoustic emission signal, or can be any other signals. So this is minimum value and maximum value. So you have, if you have trained the ANN, I think you have already got the experience that what kind of role the normalization plays, right? Right, guys? So if you use normalization, and when you train the ANN, and you can finish the training within 5 seconds, maybe 10 seconds. However, if you do not use the normalization, and you use several hours, that means normalization plays a very, very important role. And that's the reason we need to do the normalization. And how to do the normalization? So suppose I have this physical, the raw data, minimum and maximum. I use this equation and to get the normalization. And that means normalization is a mapping. It's mapping from this physical interval and to this zeta, okay? And which is located in between -1 and 1. You understand, guys? So this is called normalization. And how to do that? And we just use a very, very simple linear mapping. So linear mapping, x, the relationship, this one shows the relationship between zeta and this x. X is your raw data, and zeta is your normalized data. All right? So we use this equation. This equation says, so this first term, the average of x maximum value plus x minimum value is the first term. And the second term is x maximum minus x minimum divided by 2. Here, multiplied by zeta. All right? I think, Jessica, you can refresh your memory on how to do the linear mapping in FEM. So we use this one, and if we have x, we can calculate the data, calculate zeta, or we have zeta, we can calculate the corresponding x. We can make sure when zeta equals -1, x equals x minimum. When zeta equals +1, x equals x maximum. So the inverse function, zeta, we write zeta in terms of x is this. So let's go down. So inverse x, okay? So the inverse x. So this one, after we get this one, and we can write zeta in terms of x. So this is how we do the normalization. So you can see for our case, if we use x minimum 0, x maximum 100, x equals 50 plus 50 zeta, and then you can easily get write the zeta equals the function of the x. All right, I'm going to. I hope you can do that. This is called normalization. You understand? So after you normalize the data, and then you put this input into this is the trained ANN, and then you will get the output, right? After you get the output, because you are using the normalized input data, that means this is the output will be normalized output. Do you guys agree? Normalized output means that this is not the physical output. And then you need to do the denormalization. You know that, right? Denormalization is the inverse process. And how to do that? And we use the same thing. You can see output is a function of the input. So suppose, so T, okay? T is the result. T minimum and T maximum. So this is a physical T minimum value for the output. So this is the physical output value for this is output maximum one. And so we use this equation, the same equation, to do the normalization, and T equals the average of maximum value and this minimum value, this is 2. I'm sorry, so this is 2 here, and plus T maximum minus T minimum divided by 2 multiplied by zeta. And then this is zeta, okay? As I said, this output, because you are using normalized input, the output will be normalized output. And then you can just plug in here in this equation and to get your physical output value. You understand, guys? So in the final exam, I will ask you guys to tell me on how to do the normalization and how to do the denormalization. And then I will ask you, based on your experience, and what kind of role the normalization plays in the ALN training. You should be able to tell me these things, right? Okay, and now I'll talk about denormalization and denormalization, and then I'm going to talk about mathematically and how we implement this ALN. And we already know that we have the weight values, and we have the weight values and also bias values. And suppose you give me a data, input data, and how can we calculate this is output mathematically? So you can see here, okay? Without loss of generality for any neuron inside here, any neuron here, and how to get, suppose I have input, and then I have a weight and a bias value. I use this equation, you can see, input value multiplied by the weight value, the connection weight value, then plus B1, this guy is the bias value, then this guy equals N1. Then the N1, after the N1, after you obtain this N1, and then we put this N1 in this function, and to get A1. A1 is the output value of this neuron. You understand? And which will be fed onto next layer for here onto this output neuron. Questions? So I'm teaching how to mathematically map, how to implement this is mathematically. So one more time, okay? Without loss of generality for all these hidden neurons, and we use this equation to calculate input value multiplied by the corresponding connection value, weight value, and then plus the corresponding threshold value or bias value, then we get this N1. Then N1 is applied to this function, and this function, we get this A1. For this function, and we use 10 sig function. Do you still remember 10 sig? So this function, and we use 10 sig function. So you can use any functions, but you need to be consistent. And for our ALN, and when we check the MATLAB, and we found out we use the 10 sig. So you need to stick to, you need to keep using this 10 sig. What's the 10 sig? It is exponent function. Look at the lecture notes. All right? You use this 10 sig, and to get A1, this A1 will be the output of this is neuron, and which will be fed into next layer. And for our case, so this is A1 and goes here. Now, for this output, right, the same thing. And for this output, so this will be my input, and for this output, and use the same thing. So this A1, right, and multiplied by OW1. So multiplied by A1 multiplied by OW1. So then plus A2 from here multiplied by OW2 and so on and so forth. And for this example, and we have, this is A25 multiplied by OW and 25. And we put all of them together, and then we plus the BO, right? So this guy's bias value. You have sense? And then the total, the whole thing. Hello, it's late.
Sorry, I overslept.
Okay. So this one, so this is A25 and plus and B. So this value and will be, we just denote this one as a value. We can just as devote as this is an output, okay, an output. Then so this is total output is a total output. And will be equal this one, and will be equal to function and this NO. So here this function also the tensor function. Questions over? So today's lecture is very, very important, and because you have already know how to treat the ANN using MATLAB, and here on how to implement the trained ANN in any engineering environment, not just for IR. For IR, we just treat IR as a specialized computer. This is a MELFA BASIC V. That is a special language. For any language, for any computer language, and you can implement. And so this is a MATLAB trained ANN in any engineering application, as long as you know on how this ANN mathematically work. All right? Questions? Ricky?
So why are we applying this to the industrial robots? Like what kind of output is this, are we training it for?
Good, that's a good question. What is the bigger picture? And the ANN is used to handle uncertainties. Do you guys agree? For example, the NASA people, if we build the Mars rover or what kind of Mars these rovers, and we want to send this rover to an uncharted area, right? What uncharted area means that there's a lot of uncertainties. And how can we make sure this guy can handle these things by itself? So we need to use ANN. How to do this AI training? And we need to use this a lot of inputs and the corresponding outputs to train this guy and to know whenever this is the conditions are met, and they need to take the corresponding actions. And for the ANN, for the industrial robots, why we need to use ANN? Because when we need to use that, because I told you guys in the lecture, because the industrial robots, it has several joys, right? Have got several joys. That means this guy is very, very flexible. The bad thing is that because it is flexible and the rigidity is bad, right? Do you guys agree? Flexibility and rigidity are always competing to each other. Do you guys agree? Okay, so as a result, if you suppose I just use industrial robot, the industrial arm to polish this area. So because this arm is not very, very rigid as this is a CNN machine. So whenever, so here is some bump. Okay, this is a hand, and we'll touch the bump, and what will happen? The bump will give reaction force to the hand, right? You guys agree? Because as I said, the rigidity of the arm is bad. And then as a result, this is arm, this is the hand, will be pushed back. You agree? Once this guy is pushed back, even though it's a very small amount of pushback, and then when you finish the polishing, if you do not do anything, the final dimension of this surface will not be the dimension you are desiring, you are looking forward to, you are expecting. You guys agree? As a result, in order to get the desired surface dimension, I need to take care of the hand. Whenever, so if the bump is very, very high, okay, that means the more reaction force will be applied onto the hand. You guys agree? And then in this case, I need to teach my IR, and in this case, it just go forward, goes a little bit further down. And to make sure this is improvement, the further distance can compensate the pushback. Okay, you understand?
Yeah, so this is like to improve the precision. Of
Yeah, improve the precision.
To account for like uncertainties in the dynamics of the machine.
Yeah, uncertainty for the example I'm giving you, for the uncertainties of the bumps. Different bumps with different heights, right? Different because the different heights, and they will give different pushback force to the arm.
Got it. Okay.
You know, so today this time I just mimicking something. I did not give you sensors, and we just use a mathematical function and to mimic and how to use ANN. Okay, so for our problem, for our engineering problem here, and I give you 4 input values. The 4 input values then, and they are fed into this ANN. Finally, they get, and this is 4 output values. What I want to see is your 4 output values, and it can be demonstrated. How to demonstrate? And I ask you guys to put this is your arm, move your arm along the conveyor belt. And when this position then go this direction, I can see how much it offset. And next position, another offset. I want to see the offset amount, just visually. Okay? Any questions on how to define the ANN, how to design, build, train, and test, and how to implement the ANN in any engineering applications? Now it's time you guys to implement what I just told you in this IR. Right? I'm here if you have any questions. Let me know. So this slide is very, very important. Okay, as I said.
I think we just copy paste.
Dude, I didn't follow.
Like, you know, the example.
I think we replaced all the way to
I think so, yeah.
Then I wrote out I know, I want to tell you the water water meal. I was like,
That's good, bud.
sorry.
That's-
So I did all the boxes. Make sure that what was the so this line is all the W.
And you're gonna make this great.
There's robots going. Okay, that would be WT1. So you can't really do it like that. This gonna put them all the same. No, that's just one. One to two. It's all the way down to W2 there. That's why you need to put it in one there. All right. What things? So there's second features that you have to move. Yes. Yeah, that's why.